The transport ship's engines hummed quietly as it approached the massive structure floating in space. Emily Watson pressed her face against the small window and watched the Cathera Academic Institute grow larger with each passing moment. The building looked like someone had taken a crystal and stretched it into impossible shapes, with towers that twisted and curved in ways that hurt her eyes to follow. "First time seeing alien architecture?" asked Alex Rivera, one of her graduate students. He was trying to look calm, but Emily could see his hands shaking slightly as he gripped his tablet. "First time seeing anything alien?" Emily replied honestly. She was a mathematics professor at Earth University, specializing in chaos theory and agricultural optimization. 6 months ago, she had been grading papers in her small office. Today, she was representing humanity at the most advanced research facility in known space. The other two students, Maya Patel and Tom Bradley, were staring out their own windows with wide eyes. Maya was taking pictures with her phone, even though the officials had told them the images probably wouldn't work properly once they got inside the institute. Tom was frantically scribbling notes in a physical notebook, old-fashioned but reliable. "Remember," Emily told her students, "we're here to observe and learn. The Galactic Confederation invited us as part of their cultural exchange program. We're not expected to contribute anything significant. Just try to understand what they're doing and don't touch anything that glows." The docking process took nearly an hour. The transport had to pass through 3 different scanning fields, each one making the ship vibrate in a different way. Emily felt her teeth ache during the 3rd scan, and Alex complained that his fillings were tingling. Finally, they were cleared. To dock. The airlock opened with a soft hiss, and Emily got her first breath of alien air. It smelled like ozone and something faintly sweet, like vanilla mixed with metal. A figure approached them from across the docking bay, moving with a strange gliding motion. Dr. Selvek was Velthani, one of the species that had founded the Institute 300 years ago. His body was roughly humanoid, but made of what looked like living crystal. Faceted surfaces caught the light and threw it back in rainbow patterns. When he spoke, his voice came from a device clipped to his chest rather than from anything that looked like a mouth. "Welcome, human researchers," Dr. Selvek said. His translator gave him a slight accent that reminded Emily of her grandfather. "I am pleased to guide you through our facility. Your species' inclusion in the exchange program has generated considerable interest among our scholars." As they walked through the Institute's corridors, Emily tried not to gawk too obviously at everything around her. The walls seemed to be alive, showing holographic displays that changed as they passed. Some showed mathematical equations that stretched across entire wall sections. Others displayed what looked like star maps with moving points of light. A few showed things that Emily couldn't even begin to identify. The Institute houses researchers from 17 different species, Dr. Selvek explained as they walked. Each brings their unique perspective to the challenges of advanced mathematics and computational theory. The Ethan Collective contributes bio-neural processing networks. The Krillian Empire provides stellar core computational matrices. The Zephyrian Union offers quantum probability calculators. Maya leaned over to whisper to Emily. "I understood maybe half of those words. I got math and computers," Tom whispered back. "I think that's the important part." Dr. Selvek led them to an observation deck that looked down into a vast chamber. Emily felt her breath catch in her throat. The room below them contained what looked like a small galaxy. Points of light swirled in complex patterns, connected by streams of energy that pulsed and shifted in rhythm. The whole thing was beautiful and terrifying at the same time. "This is our primary achievement," Dr. Selvek said with obvious pride. "The Nexus Array. It processes mathematical challenges that would be impossible for any single species to solve. The computational power contained in this chamber exceeds the total processing capacity of most civilizations." Alex pointed at a section where the lights seemed to be spinning faster than the rest. What's it working on right now? Currently, the array is attempting to solve optimization challenges related to resource distribution in chaotic environments. The problem has been running for 18 standard months without resolution. Dr. Selvek's crystalline body dimmed slightly, which Emily had learned was their equivalent of a frown. It represents one of the most complex mathematical challenges ever attempted. 18 months? Maya asked. What kind of problem takes 18 months to solve? The type of problem that has frustrated our greatest minds across multiple species, Dr. Selvek replied. Tomorrow, you will have the opportunity to observe a presentation on this challenge. The grand mathematician of the Ethon Collective will explain why this particular problem has proven so resistant to solution. As they continued the tour, Emily found herself thinking about the problems she assigned her students back home. Agricultural optimization, resource management under uncertainty, chaos theory applications to farming systems. The math could get pretty complex, but 18 months seemed excessive for any computational problem. They visited laboratories where researchers from different species worked on various projects. In one room, beings that looked like walking trees were growing crystals that somehow performed calculations. In another, creatures that resembled metallic spiders were weaving what Dr. Selvek called probability nets. Everything was fascinating and completely beyond Emily's understanding. The day ended with dinner in a cafeteria that served food suitable for dozens of different biological systems. Emily and her students ate something that tasted like chicken, but was apparently grown from modified algae. The other diners included species Emily had never seen before, some of which didn't seem to eat food at all, but instead absorbed energy directly from charged plates. This is incredible, Tom said between bites. I mean, I don't understand 90% of what we've seen today, but it's incredible. I keep thinking about that computational array, Alex said. All that processing power working on one problem for 18 months. It must be something really extraordinary. Emily nodded, but something was nagging at her. The description of the problem sounded familiar somehow. Resource optimization in chaotic environments with biological interference. She had assigned problems like that to her graduate seminars. Admittedly, they were challenging, but 18 months of supercomputer time seemed like overkill. Tomorrow should be interesting, she told her students. Let's see what kind of problem has the galaxy's smartest species stumped. The morning alarm in Emily's quarters sounded like wind chimes mixed with distant thunder. She had barely slept, partly because the bed was designed for a species with different spine curvature, and partly because her mind kept turning over everything she had seen the day before. The sheer scale of the Nexus array kept coming back to her, all that computational power focused on a single problem. Her students met her in the corridor outside their rooms, all looking as tired as she felt. The artificial day-night cycle at the Institute didn't quite match Earth normal, and their bodies were still adjusting. Maya was drinking something from a dispenser that smelled like coffee but looked purple. Tom was eating what appeared to be geometric shapes that crunched like cereal. Ready for the big presentation? Alex asked. He had dark circles under his eyes but seemed excited despite the lack of sleep. Dr. Selvek met them at the entrance to the main auditorium. The space was enormous, designed to accommodate species of various sizes and environmental needs. Some sections were filled with a thick orange atmosphere. Others were partially flooded with liquid that glowed softly. The human section was mercifully normal, with regular air and standard seating. The presentation you will witness today, Dr. Selvek explained as he guided them to their seats, represents the culmination of our greatest collaborative effort. Researchers from 12 species have contributed to understanding this problem, and the Nexus array has dedicated unprecedented processing time to finding a solution. The auditorium was filling with beings Emily couldn't have imagined in her wildest dreams. Creatures that looked like living smoke drifted into the atmospheric sections. Things that resembled giant flowers with too many eyes settled into spaces filled with that glowing liquid. Near the human section, A group of beings that looked like walking crystals, similar to Dr. Selvek, took their places. At the center of the auditorium, a massive holographic display materialized. Emily had seen holography before, but nothing like this. The image was so detailed and three-dimensional that it seemed like looking at a real miniature world. She could see continents, weather systems, and what looked like cities connected by transport lines. A being Emily had never seen before approached the center stage. It was roughly humanoid, but covered in patches that glowed and pulsed with different colors. When it spoke, the patches changed intensity in patterns that seemed to match its words. "I am Grand Mathematician Thylex of the Ethon Collective," the being announced. Its voice came from speakers throughout the auditorium, translated into dozens of languages simultaneously. For the past 3 galactic cycles, our combined intellectual resources have focused on a challenge that has tested the limits of our understanding. The holographic display shifted, zooming in on one of the continents. Emily could see terrain that changed from mountains to forests to what looked like farmland. Weather systems moved across the landscape in real time, bringing rain to some areas while others remained dry. In the populated areas, resources appeared as colored dots that moved and changed based on some complex pattern. "The problem is this," Thylex continued, its light patches pulsing brighter. "How do we optimize resource collection and distribution across multiple sites when those sites are subject to chaotic environmental variables, unpredictable biological interference, and gravitational fluctuations that affect transport efficiency?" Maya nudged Emily. "Professor, this looks like something we've seen before." Emily was thinking the same thing. The display showed agricultural areas affected by weather patterns, transport routes that had to adapt to changing conditions, and resource yields that varied based on seasonal and biological factors. It reminded her strongly of the agricultural modeling problems she taught in her advanced seminars. "The complexity increases exponentially," Thylex explained as the display zoomed out to show multiple continents, "when we consider that each site affects the others through trade relationships, shared transport networks, and biological systems that cross territorial boundaries. The biological interference patterns alone involve over 40 different species with seasonal migration patterns, reproductive cycles, and territorial behaviors." A new speaker took the stage, one of the crystalline Veltani. "Our quantum processing networks have generated 847 billion possible solutions over the past 18 months. The highest efficiency rating achieved by any solution is 12.3%. Most solutions fall below 8% efficiency." Tom leaned over. "Are they talking about crop rotation and pest management?" "I think so," Emily whispered back. "But they're making it sound like rocket science." The presentation continued for another hour, with researchers from different species explaining how their particular computational approaches had failed to solve the problem. The bio-neural networks couldn't handle the chaotic variables. The quantum processors got lost in the infinite possibility space. The stellar core matrices overheated, trying to calculate all the biological interactions. "The fundamental issue," concluded a speaker that looked like a mechanical spider, "is that biological systems resist mathematical prediction. The interference patterns appear random but contain hidden structures that our models cannot detect. The chaotic environmental factors create feedback loops that amplify small changes into system-wide effects." Emily found herself nodding along. Everything they were describing was basic chaos theory applied to agricultural systems. The hidden structures in biological patterns were well-understood concepts in earth farming. Farmers had been dealing with chaotic feedback loops for thousands of years. Therefore, Thylex announced, its patches flashing in what Emily assumed was a dramatic flourish, "We must conclude that this optimization problem may be fundamentally unsolvable using current mathematical frameworks. The Nexus array will continue processing, but we estimate the probability of achieving greater than 15% efficiency to be effectively zero." The auditorium filled with sounds that Emily guessed were the alien equivalent of disappointed murmuring. Some species flickered their lights, others changed colors, and a few made noises that the translators didn't even attempt to interpret. Dr. Selvek turned to the human delegation. As you can see, this represents the absolute cutting edge of mathematical complexity. Problems like this demonstrate why the Institute exists. Only by combining the greatest minds from across the galaxy do we have any hope of making progress on such challenges. Emily looked at her students. Alex was staring at the display with a puzzled expression. Maya was taking notes on her tablet, but Emily could see she had written farming optimization with several question marks. Tom was sketching the resource distribution patterns in his notebook. Dr. Selvek, Emily said carefully, would it be possible for us to get a closer look at the problem parameters? As educational observers, of course. Certainly, Dr. Selvek replied, though I should warn you that the mathematics involved are quite advanced. Your species may not have encountered complexity of this level before. Emily smiled politely. We'll do our best to follow along. As the other attendees began filing out of the auditorium, Emily and her students moved closer to the display. The more Emily looked at the problem, the more familiar it became. Weather-dependent resource availability, biological interference, patterns, optimization across multiple sites with varying conditions. She had assigned almost exactly this problem to her graduate seminar just 6 months ago. Her students had solved it in 2 weeks. Emily stood in front of the holographic display, watching the patterns of resource distribution shift and change across the alien landscape. The more she studied it, the more certain she became. This wasn't some incomprehensibly advanced mathematical challenge. This was a farming optimization problem, dressed up in fancy alien terminology, but fundamentally the same type of challenge she had been teaching for 15 years. Dr. Watson, Alex said quietly, this is definitely the same type of problem you gave us last semester, right? Not just the same type, Emily replied, keeping her voice low. I think this is almost exactly the problem I assigned to your agricultural systems class. The only difference is they're calling the farm's resource collection sites and the pests biological interference patterns. Maya was scrolling through her tablet, pulling up old assignment files. Here it is. Optimize crop yields across multiple sites, accounting for weather variability, pest migration patterns, soil quality changes, and inter-site resource sharing. That's basically what they just spent 2 hours describing. Tom looked around nervously. Should we tell them? Emily considered this carefully. They were guests here, representing humanity in what was supposed to be a learning exchange. The last thing she wanted to do was embarrass their hosts by pointing out that their impossible problem was undergraduate homework at Earth universities. On the other hand, the aliens seemed genuinely stuck, and maybe a different perspective could help. Dr. Selvek approached their small group, his crystalline form, refracting the light from the display into rainbow patterns. I hope the presentation was educational for your species. The mathematical concepts involved are quite sophisticated. It was very illuminating, Emily said diplomatically. I was wondering if we could get more specific details about the optimization parameters. What exactly are you trying to maximize? Resource collection efficiency across all sites simultaneously, Dr. Selvek replied, while maintaining sustainability of the biological systems and accounting for transport costs affected by gravitational and environmental variables, and the biological interference patterns, seasonal migration of resource-consuming organisms, reproductive cycles that affect local resource availability, territorial behavior that blocks access to certain sites, and symbiotic relationships that can either enhance or reduce resource yields depending on management approaches. Maya caught Emily's eye and mouthed the word bugs. That's what they were talking about. Insects, birds, small mammals, and other creatures that affected crop yields. The aliens had made it sound like some exotic phenomenon, but every farmer on Earth dealt with these exact issues. The environmental variables seem complex, Emily said, still fishing for information. What kind of factors are we dealing with? precipitation patterns that vary seasonally and geographically, temperature fluctuations that affect both resource, growth rates and biological activity, wind patterns that influence both environmental conditions and organism movement, and soil quality variations that change over time based on usage and environmental factors. Tom wrote something in his notebook and showed it to Emily. Weather, climate, and soil quality. Dr. Selvek, Emily said carefully, would it be possible for my students and me to examine the raw data? Not to interfere with your research, of course, but as a learning exercise. We might be able to understand the problem better if we could see the underlying mathematics. Dr. Selvek's form brightened slightly, which Emily had learned was a positive response. That would be acceptable. The Institute encourages cross-species academic exchange. Perhaps examining our data will help your species understand the level of complexity involved in truly advanced mathematical research. 20 minutes later, Emily and her students were seated at a workstation in one of the Institute's research labs. The interface was alien in design, but intuitive enough to use. Emily found herself looking at data sets that confirmed everything she had suspected: temperature ranges, precipitation data, soil composition analyses, and biological population surveys. Everything a farmer would need to plan crop rotations and pest management strategies. This is incredible, Alex said, but not in the way Dr. Selvek probably expected. They have more detailed data than most Earth agricultural research stations. Look at this biological survey data. They've tracked migration patterns for dozens of species over multiple years. The weather modeling is amazing, too, Maya added. They have predictive models that go out months in advance. Most Earth farmers would kill for data this good. Emily was examining the transportation cost calculations. They've even factored in seasonal variations in transport efficiency. This is like having perfect information for a farming operation. So why can't they solve it? Tom asked. If they have all this data, why are their supercomputers struggling with something we do as homework? Emily thought about this as she scrolled through more of the data. The information was comprehensive and accurate. The computational resources were far beyond anything Earth had available. The mathematical frameworks the aliens were using were sophisticated and theoretically sound. So what was the problem? I think I know what's wrong, Emily said slowly. Look at their solution approaches. She pulled up the files describing the various computational methods the aliens had tried. The quantum processors were attempting to calculate every possible outcome simultaneously. The bioneural networks were trying to model each biological variable with perfect precision. The stellar core matrices were brute forcing through every mathematical combination. They're trying to solve for perfection, Emily realized. They want a solution that accounts for every variable, predicts every change, and optimizes every outcome. They're treating this like a physics problem with exact solutions. But farming isn't like that, Maya said. You can't predict everything. Weather changes, bugs show up where they're not supposed to be, soil conditions vary from field to field. You have to build flexibility into the system. Exactly, Emily said. They're looking for the mathematically perfect solution to a problem that doesn't have one. What they need is a good enough solution that can adapt to changing conditions. Alex was reading through more of the computational approaches. Look at this. They've been running scenarios for 18 months trying to find the optimal solution for all possible conditions simultaneously. No wonder they're stuck. Emily pulled up her own files on her laptop, looking for the agricultural optimization algorithms she had developed for her classes. The math was much simpler than what the aliens were using, but it was designed for the real world where perfect information didn't exist and conditions changed constantly. Dr. Selvek, Emily called over to where their guide was observing from, across the lab. Would it be acceptable for us to try running our own analysis of this data? Just as a learning exercise to see how our mathematical approaches compare to yours. Dr. Selvek glided over to their workstation. Your species wishes to attempt analysis of this problem. I should warn you that our greatest computational resources have been unable to achieve significant progress. We understand, Emily said. We're not expecting to solve anything. We just want to see how our mathematics handle this type of challenge. It would help us understand where our approaches are limited. Very well. The Institute encourages all forms of academic inquiry. You may proceed with your analysis. Emily looked at her students. Ready to show them how farmers think about math? Let's do it, Alex said, cracking his knuckles. Time to solve their impossible problem with sophomore-level chaos theory. Emily cracked her knuckles and opened her laptop, while her students gathered around the alien workstation. The interface looked like something from a science fiction movie, but the underlying data was familiar territory. She had been teaching agricultural optimization for 15 years, and this problem, despite its alien dressing, was right in her wheelhouse. Okay, Emily said, addressing Dr. Selvek and the few other alien researchers who had gathered to watch. The issue I see with your computational approaches is that you're trying to solve for optimal outcomes under all possible conditions. But that's not how farming works in the real world. Please explain, Dr. Selvek said. His crystalline form had dimmed slightly, which Emily interpreted as polite skepticism. On Earth, we call this type of challenge agricultural resource management, Emily explained as she began translating her algorithms into the alien computer system. Farmers have been dealing with chaotic weather patterns, unpredictable pest behavior, and variable soil conditions for thousands of years. The key insight is that you don't try to predict everything. Instead, you build systems that can adapt to whatever actually happens. Maya pulled up her own laptop and started running parallel calculations. Professor Watson taught us to think of farming as managing uncertainty rather than eliminating it. You create resilient systems that work reasonably well under a wide range of conditions, rather than perfect systems that only work under ideal conditions. Tom was sketching diagrams in his notebook, showing crop rotation patterns and pest management strategies. It's like the difference between building a bridge that can handle exactly 100 tons and building a bridge that can handle anything from 50 to 150 tons. The second approach is more practical even if it's not mathematically optimal. One of the alien researchers, a being that looked like a collection of metal tentacles, asked, "But surely precise optimization yields superior results to approximate methods?" "Not necessarily," Alex replied. "Especially when your data has inherent uncertainty. If your weather predictions are accurate within 10%, there's no point in optimizing to the nearest 0.1%. You're just optimizing noise." Emily had finished inputting her basic agricultural optimization algorithm and was adapting it to the alien data format. The mathematics we use on Earth are called chaos theory and robust optimization. Instead of finding the single best solution, we find solutions that perform well across a range of conditions and can adjust when conditions change. She executed the program, and almost immediately, results began appearing on the display. The alien workstation processed her relatively simple algorithms in seconds, generating resource distribution patterns that achieved 67% efficiency. The lab fell silent. Dr. Selvek's crystalline form was pulsing with light patterns that Emily didn't recognize. Several other aliens were making sounds that the translators couldn't interpret. "This must be an error," said Grand Mathematician Thylex, who had arrived while Emily was working. "Our stellar core matrices achieved only 12% efficiency after 18 months of calculation." "No error," Emily said, checking her results. "This is standard agricultural optimization math. Maya, want to show them your advanced version?" Maya nodded and took over the workstation. "I wrote my master's thesis on adaptive resource optimization under climate uncertainty. Let me run my algorithms on their data." Maya's program was more sophisticated than Emily's basic version, incorporating machine learning elements that could improve performance over time. When she executed it, the efficiency rating climbed to 74%. "Impossible," whispered one of the alien researchers. "The biological interference patterns alone should make this level of efficiency unattainable." Not if you account for them properly, Tom said, pulling up his notebook drawings. Look, you're treating pest migration like it's completely random, but it's not. There are patterns based on food availability, breeding cycles, and seasonal changes. Earth farmers have been tracking these patterns for centuries. Alex had connected his laptop to the display and was showing the aliens his simulation models. The trick is to work with the biological systems instead of fighting them. Some of what you call interference patterns can actually be beneficial if you manage them right. Certain insects are pollinators, some animals distribute seeds, and natural predator-prey relationships can control pest populations. Emily watched the alien researchers examining their results with what she assumed were expressions of shock and confusion. The fundamental difference in our approaches is that you're trying to impose perfect order on a chaotic system. We're trying to find order within the chaos. But your mathematics are so simple, Dr. Selvek protested. Our quantum processing networks use computational frameworks that represent the cutting edge of mathematical theory. Sometimes simple works better, Emily replied, especially when you're dealing with systems that are inherently unpredictable. On Earth, we have a saying, the best is the enemy of the good. Your computers were looking for the perfect solution to an imperfect problem. Maya had finished running additional optimization cycles, and the efficiency was now approaching 78%. This is actually pretty good performance for a first run. In a real farming situation, we would collect actual performance data and refine the models over time. I bet we could push this into the 80s with a few seasons of real-world feedback. 80% efficiency? Thylex's light patches were flashing in rapid patterns. That would revolutionize resource management across 17 star systems. It would revolutionize a lot more than that, said a new voice. Emily turned to see a massive creature entering the lab, something that looked like a cross between a bear and a crystal formation. I am Director Kethlin of the Institute. Word of your achievement has spread rapidly through our research networks. Emily felt suddenly uncomfortable. Achievement might be too strong a word. We just applied some basic Earth mathematics to your problem. Basic mathematics that accomplished what our most advanced computational resources could not, Director Kethlin replied. Tell me, how long did it take your species to develop these techniques? Well, Emily said, thinking about it, humans have been practicing agriculture for about 10,000 years. The formal mathematical frameworks we use today were developed over the past century or so, building on centuries of practical farming knowledge. And how long did it take you to solve our specific optimization problem? Emily looked at her watch. About 45 minutes. The lab erupted in sounds and light patterns from the various alien species. Emily was pretty sure some of them were expressions of amazement, though a few might have been alarm. Dr. Watson, Director Kethlin said, I believe we need to discuss the implications of what you have demonstrated today. Your species may have capabilities that we have significantly underestimated. Tom raised his hand tentatively. Actually, this isn't even our best work. This is like freshman-level agricultural mathematics. Professor Watson has graduate students working on much more complex optimization problems. Such as? Dr. Selvek asked. Maya grinned. Multi-planetary agricultural systems with variable gravity and atmospheric conditions, terraforming optimization for hostile environments, closed-loop ecosystem design for generation ships. You know, the advanced stuff. Emily watched the alien researchers process this information. She was beginning to realize that what seemed like normal academic problems to humans might be incomprehensibly advanced to species that had evolved on more stable, predictable worlds. I think, she said slowly, we need to have a longer conversation about the differences between Earth mathematics and galactic mathematics. The conference room was packed with beings Emily couldn't have imagined a week ago. Representatives from 12 different species had gathered to hear about the human solution to what had been considered the most challenging optimization problem. In galactic academia, Emily sat at the head of a curved table that adjusted its height and shape to accommodate the various alien physiologies surrounding it. Director Kethlin had called this emergency meeting after word spread through the institutes, research networks, that humans had solved the impossible problem in less than an hour. Emily was still trying to process the fact that what she considered basic agricultural mathematics had apparently revolutionized galactic computational theory. "Before we begin," Director Kethlin announced, "I want to ensure that all species representatives understand the significance of yesterday's demonstration. The human researchers achieved 78% optimization efficiency on a problem that has consumed our greatest computational resources for 18 months without exceeding 12% efficiency." A wave of sounds and light patterns swept through the room. Emily was getting better at reading alien body language, and she was pretty sure most of them were expressing variations of disbelief. Grand Mathematician Thylex spoke first. "Director Kethlin, with respect, there must be some error in the human calculations. It is mathematically impossible for such simple algorithms to outperform our advanced computational matrices." "That's what we thought too," Emily replied. "So we double-checked our work." "Alex, want to show them?" Alex connected his laptop to the room's display system. "We ran the calculations 3 more times using different approaches. We also tested our algorithms against Earth agricultural data to make sure they were working correctly. Same results every time." The display showed side-by-side comparisons of the alien computational approaches versus the human agricultural optimization methods. The difference in efficiency was stark, but what was even more striking was the difference in computational complexity. The alien algorithms were using processing power equivalent to small stellar cores. The human algorithms ran on equipment that could fit in a backpack. "This is what we don't understand," said a researcher that looked like a mechanical spider. "Your computational resources are primitive by galactic standards, yet you achieve superior results. How is this possible?" Maya stood up and walked to the display. "I think the key difference is in how we approach the problem. You're trying to create perfect models of imperfect systems. We're trying to create imperfect models that work well enough in imperfect systems." She pulled up a comparison showing the alien weather prediction models versus Earth farming practices. "Your weather modeling is incredibly sophisticated. You can predict atmospheric conditions months in advance with remarkable accuracy. But farmers don't need perfect weather predictions. They need to know how to respond when the weather doesn't match the predictions." Tom added his notebook drawings to the display. "Same thing with biological interference. You're trying to model every possible pest behavior with perfect precision. Earth farmers assume pests will do unexpected things and plan accordingly. We don't try to predict exactly where every bug will be. We just make sure our crops can handle whatever the bugs actually do." Dr. Selvek's crystalline form was pulsing with what Emily had learned was deep confusion. "But surely precise modeling yields better results than imprecise planning." "Not when the system you're modeling is inherently chaotic," Emily explained. "Earth is what we call a death world. Everything on our planet is trying to kill everything else. Weather patterns are violent and unpredictable. Biological systems are incredibly complex and often hostile. Geological activity can change conditions overnight." She pulled up images from Earth showing hurricanes, volcanic eruptions, locust swarms, and other natural disasters. "When you grow up trying to grow food on a planet that's actively trying to kill you, you get very good at optimization under uncertainty. You learn to build systems that can survive surprises. This explains much about human psychology," observed a being that looked like living smoke. "Your species approaches problems assuming failure is likely, and success requires adaptation." "Exactly," Alex said. "We don't try to prevent all failures. We try to build systems that can recover from failures quickly." Director Kethlin gestured to the data still showing on the display. "The implications of this approach extend far beyond agricultural optimization. Our trade route planning, resource allocation, and even military logistics are based on optimization models that assume relatively stable conditions. While human models assume unstable conditions," Emily added, "which probably makes them more robust in real-world applications. Grand mathematician Thylex's light patches were flashing in rapid patterns. Dr. Watson, you mentioned that this agricultural optimization problem was assigned as homework to your students. What level of students? Graduate level, Emily replied, though some of the concepts we start teaching in undergraduate courses. And how long do students typically take to solve such problems? Emily thought about it. For the basic version we solved yesterday, usually 1 to 2 weeks. For more advanced versions like Maya's adaptive algorithms, maybe a full semester. The room fell silent except for various alien sounds that Emily assumed were expressions of shock. She was beginning to understand that the galactic academic community had fundamentally different expectations about problem complexity and solution timeframes. Dr. Watson, Director Kethlin said slowly, what do you consider to be advanced mathematical problems for your students? Emily exchanged glances with her students. Well, advanced undergraduate problems might include multi-crop rotation optimization under climate change scenarios. Graduate-level problems could be terraforming algorithms for hostile environments, or closed-loop ecosystem design for generation ships, or resource optimization for multi-planetary agricultural systems. Multi-planetary agricultural systems, repeated the mechanical spider researcher. You teach students to optimize resource distribution across multiple worlds? It's mostly theoretical, Maya said, though some of the concepts are being used for Mars colonization planning. Tom flipped through his notebook. My senior thesis was on agricultural optimization for tidally locked planets. You know, worlds where one side is always hot and the other side is always cold. Tidally locked planets, Dr. Selvek whispered. Conditions so extreme that we have never attempted to model agricultural systems for such environments. It's not that hard, Tom replied. You just have to account for extreme temperature gradients and work with the natural convection patterns. The math gets interesting when you factor in atmospheric circulation, but it's still just applied chaos theory. Alex pulled up another file. I'm working on my dissertation about agricultural systems for brown dwarf planets, places with no star at all, just geothermal energy. Professor Watson says it's good practice for really hostile environments. Emily watched the alien representatives process this information. She was starting to realize that what humans considered normal academic exercises were apparently beyond the computational capabilities of the galaxy's most advanced civilizations. Let me make sure I understand correctly, Director Kethlin said, carefully. Your undergraduate students routinely solve optimization problems for planetary environments more hostile than anything we have attempted to model. Well, yes, Emily replied. Earth students grow up thinking about survival in hostile environments. It's natural for them to extend those concepts to other hostile environments. Most of our agricultural mathematics assumes that conditions will be terrible and unpredictable. Because conditions on Earth are terrible and unpredictable, Maya added helpfully. A new voice joined the conversation. May I ask what you consider to be an easy problem? The speaker was a being Emily hadn't seen before, something that looked like a crystal tree with roots that extended into the floor. Emily thought about her introductory courses. Easy problems would be single-crop optimization in stable climates, or resource allocation with reliable supply chains, or biological system modeling where the organisms are cooperative rather than competitive. Cooperative biological systems, the crystal tree repeated. Such things exist on your world? Not many, Tom said. Most Earth biology is based on competition for resources. Plants compete for sunlight and water. Animals compete for food and territory. Microorganisms compete for everything. Cooperation exists, but it's usually temporary and based on mutual benefit rather than genuine cooperation. This explains why your optimization algorithms assume biological interference, Dr. Selvek observed. Your models incorporate competition as a fundamental assumption. Right, Emily said. While your models seem to assume that biological systems will behave in orderly, predictable ways. That works fine if you evolved on worlds where biological systems are actually orderly and predictable. But most worlds in the galaxy are not like Earth, Director Kethlin said thoughtfully. Most inhabited worlds have relatively stable climates, cooperative ecosystems, and predictable biological patterns. Which means your mathematics evolved to handle predictable problems efficiently, Alex said, while our mathematics evolved to handle unpredictable problems robustly. Maya was scrolling through her files. Professor, should we show them the really advanced stuff? Like the generation ship ecosystem models? Emily hesitated. If basic agricultural optimization had caused this much of a stir, she wasn't sure the galactic academic community was ready for humanity's more advanced mathematical concepts. Perhaps we should start smaller, Emily said diplomatically. Maybe we could collaborate on some intermediate problems, work our way up to the more complex applications. Dr. Watson, Grand Mathematician Thylek said, its patches flashing in what Emily was learning to recognize as excitement. Would your species be willing to establish a permanent research exchange? We have much to learn from your mathematical approaches. And we have much to learn from your computational resources, Emily replied. I think collaboration could benefit everyone. Director Kethlin stood up, which was impressive given that it was the size of a small building. I propose that we establish the Institute's first Deathworld Studies program. Dr. Watson, would you be willing to serve as the founding director? Emily looked at her students, all of whom were grinning broadly. I think that could be arranged. Excellent, Director Kethlin said. I should warn you, however, that applications from human universities to join our exchange programs have increased by several thousand% since word of yesterday's demonstration spread through galactic academic networks. Several thousand%? Emily asked. Apparently, every major university on Earth wants to send students to study at the Institute. They are particularly interested in what they call easy galactic problems that might serve as good undergraduate exercises. Tom laughed. Wait until they see the physics and engineering problems here. If their math is optimized for stable conditions, their technology probably is too. What do you mean? Dr. Selvek asked. Alex was already pulling up files on his laptop. Well, if you've never had to deal with extreme weather, seismic activity, corrosive atmospheres, or biological contamination, your engineering probably isn't designed for those conditions. Earth engineering assumes that everything will go wrong eventually. We build redundant systems, Maya added. Multiple backups, failure-resistant designs, equipment that can function even when it's partially damaged. Emily realized that the agricultural optimization problem was probably just the beginning. If galactic civilizations had evolved on stable, predictable worlds, then their entire approach to technology, engineering, and problem-solving would be fundamentally different from humanity's approach. I think, Emily said slowly, we're going to need a much bigger exchange program. 6 months later, Emily stood on the observation deck of the expanded institute, watching construction crews from a dozen species working on new research facilities. The Deathworld Studies program had grown from a single department to an entire academic division. Human professors were teaching chaos mathematics to alien graduate students, while Earth engineering students were learning to build technology that could function on hostile worlds. The agricultural optimization problem that had started everything was now used as a standard homework assignment in introductory chaos theory courses. What had once been considered the galaxy's most challenging mathematical problem was now something that first-year students solved as practice exercises. Emily's tablet chimed with a message from Earth. Another university wanted to send a delegation to study galactic physics problems. Apparently, the rumor was spreading that alien physics was much easier than Earth physics, since it didn't have to account for the chaotic conditions that Earth scientists considered normal. Professor Watson, Alex called from across the deck. "The Velthani want to know if you can help them with their stellar engineering optimization problems. They've been working on them for 3 centuries. Emily sighed and smiled. "Tell them I'll take a look, but it's probably just another homework problem." As she walked back inside the Institute, Emily reflected on how much had changed. Humanity had come here expecting to learn from superior alien civilizations. Instead, they had discovered that growing up on a death world had made them exceptionally good at solving problems that seemed impossible to everyone else. It turned out that when your homework included surviving on a planet that was actively trying to kill you, everything else seemed manageable by comparison.